Hello, this is Mrs. Bentley, and I'm here to work through the Math 1 Unit 4 test review with you. So if you take a look at the first section of the test, you are working with simplifying expressions using all the laws of exponents we've been learning. And in our first problem, I notice I have a base A raised to the -2 power, and we're raising it to another power, -6. So our rule when we raise a power to a power is to multiply your exponents. So this becomes A -2 times -6. So this is going to simplify to A to the +12th. Since our exponent becomes positive, there's no need to bring it under the line or change the sign. That is your final answer. For number 2, we're multiplying two expressions. So we're going to multiply the numbers like we've always learned to multiply numbers, 3 times 8. We're going to multiply the like bases, x to the -2 times x to the 15th. And the rule when we multiply the same base is you would add your exponents. 3 times 8 simplifies to 24, and -2 plus 15 simplifies to x to the 13th power. Again, our exponents are positive, so no need to write the expression. Okay, for number 3, we have a couple different ways we could approach this problem. We could go through and raise everything in the first group to the second power, go through and raise the second group in the parentheses to the -3 power, or you could go ahead and bring down the 4a to change the -3 exponent to a +3. So that's what I'm going to choose to do. So I'm going to keep the 2a squared, and I'm going to leave this just written the way it is on the first step. And then I'm going to move my 4a base to the denominator so that I can change the -3 to a +3. And then we'll go through and now actually simplify. So remember, when you square a number, the exponent tells you how many times to multiply that number. So 2 times 2 simplifies to 4. You're going to multiply your exponents. So you're going to multiply the 2 times 2. So this simplifies a to the 4th. And on the bottom, we're going to actually raise everything to the 3rd power. So remember, that means 4 times 4 times 4. Well, 4 times 4 is 16, and 16 times 4 simplifies to 64. And then the a has an understood exponent of 1. 1 times 3, so this simplifies to a cubed. Now we need to check to see, can we simplify this expression one step farther. So if you look, we have 4 over 64. 4 is smaller than 64, so we can't divide, but we can reduce the fraction. 4 and 64 are both divisible by 4. And if you divide 4 by 4, you're going to get 1. And then 64 divided by 4 is 16. And our rule for the exponents is when we divide the same variable base, we subtract our exponent. So you're going to say 4 minus 3, so we get a to the +1. Now, when you have a coefficient of 1 or an exponent of 1, those are understood. So you may see this answer simplified all the way to just a over 16. On your test, we would accept either answer. Okay, let's take a look at number 4. Number 4, there's a lot going on in this equation. It can be a little overwhelming at first, but I notice that there is a base with an exponent that we have in common in both our numerator and denominator. So if you think about what happens, this 3 squared, if we simplify, is a 9. This 3 squared is also a 9, and 9 divided by 9 is just 1. So those two are going to equal 1. X to the 0 power, that's just going to equal 1. So really all we have left now is the y to the -4 over the y squared, and then we're going to raise everything to the second power. So you're going to take the y to the -4, and you're going to raise it to the second power over y squared, also raised to the second power. So now let's simplify. So our rule is to multiply the exponents, so this simplifies to y to the -8 divided by y to the 4th. When we divide, our rule is to subtract our exponents. So we're going to say -8 minus 4. This equals y to the -12th. And now we need to correct the negative exponents. So we need to write this under 1. So our final answer is going to be 1 over y to the 12th power. Okay, and number 5, we're back to multiplying. Notice we have a number base in each group and we have a variable base. So again, you can group your numbers and multiply 3 times 4. You're going to group your x squared times x to the negative 3, and when you multiply the same base, you're going to add your exponents. So 3 times 4 will simplify to 12. 2 plus negative 3 simplifies to negative 1. So we're going to keep the 12 in the numerator, but we need to bring down the x to the negative 1 to change the exponent to positive. So our final answer is 12 over x. Okay, in number 6, we have x cubed times y to the negative 2 times z to the 0 power. So again, I notice there's no operation and there are no bases that are the same, so we're just going to have to rewrite this expression in simplified form. So x to the 3rd power has a positive exponent, so we're going to leave it where it's at. The y to the negative 2, I'm just going to circle it and draw an arrow that I'm going to bring this base down, and z to the 0, that just equals 1. So our final answer is just going to be to keep the x cubed in the numerator and bring the y squared under the line so we can change the sign. Okay, in number 7, there's a couple different orders you could go in. I do notice inside the parentheses that I have 2 bases that are the same. So we could go ahead and multiply the d squared times the d to the negative 2. And when you add 2 plus negative 2, that's actually d to the 0, which equals 1. So these two actually end up canceling out, leaving us with just the f to the negative 6th raised to the negative 3. And when you multiply negative 3 times negative 6, this simplifies f to the 18th power. No need to move since our exponent became positive. Okay, number 8, we have a quotient, and we're raising everything to the negative 4. So we could go ahead and flip-flop these to make the exponent become positive. So basically you take the b to the 8 and you move it to the numerator. You take the a to the 4th, move this to the denominator, and that allows us to change the outside exponent to a positive. Now you're going to raise each exponent to a power by multiplying. So 8 times 4 becomes b to the 32nd power over 4 times 4, a to the 16th power. So I just took this 4 and I multiplied it times the 8 and I multiplied it times the 4. The exponents are positive, so that is the final answer. Okay, and number 9, we're dividing. We have 3 divided by 2. 3 is not divisible by 2, and they do not have any common factors, so we cannot simplify 3 over 2. We'll just keep that. If you look at your r's, you have, let me just write this out, you have your r to the 3rd power, and you're going to subtract a negative 3. So remember, when you subtract a negative, it becomes 3 plus 3. We have s to the negative 5th power, and we are subtracting a negative 5, so this becomes negative 5 plus 5. And we have t to the 1 power minus 4. So now if we go across and kind of simplify, we still have our 3 in the numerator. 3 plus 3 simplifies to r to the 6th. Negative 5 plus 5 is 0, so this just becomes a 1. T to the 1 minus 4 is going to give us negative 3, so we're going to have to bring the t to the 4th power under the line to change the sign. And the last one, number 10, we have a power to power, so the rule is to multiply your exponent, so we're going to multiply negative 4 times 4. This simplifies to a to the negative 16th, and now we just need to rewrite this to make our exponent positive. So our final answer is 1 over a to the 16th power. Okay, in questions 11, 12, and 13, we are asked to tell whether each relation is a function. We're going to state the domain and range. We're also going to identify the end behavior and determine if the function is increasing or decreasing. So since number 11, all we're given is the table of values. There's no equation here. So we're just going to write the domain and range as discrete values. So remember, your domain will be all of your x coordinates. So we're just going to list those. 1, 2, 3, 4, and 5. Your range, 2, 4, 8, 16, 32. If you notice, as our domain values are increasing, our y values are also increasing, so this function is increasing. Okay, number 12, we're given a graph. So remember, we've talked about how exponential functions will always have a domain of all real numbers. You'll see that we have an arrow on the left, so we're going to negative infinity, and we have an arrow on the right, so we're approaching positive infinity. So for your domain, you can say all real numbers. You may have been taught to write it as x is greater than negative infinity, but less than positive infinity, or you can write out the words all real numbers. Now, as you look at the range we do have a boundary. We have our horizontal asymptote, and our horizontal asymptote is crossing the axis right at -2. So even though it looks like the function is touching where y equals -2, it's actually not. It's getting very small and as close to -2 as it possibly can, but it's never going to actually equal -2. And notice the boundaries at -2, and our function is above. So here's our boundary. Our function is above, so we write our range as y is greater than -2. Okay, for in behavior, as x is approaching negative infinity, so as we read our graph going to the left, we're looking at the left arrow on the function, and notice this is where the arrow is leveling out at that horizontal asymptote. Because the horizontal asymptote is at -2, we would say the function is approaching -2. On the right side of the graph, notice the arrow is going up to infinity, so we are approaching positive infinity as x approaches positive infinity. When you look at the graph, you read the graph from left to right. Notice as my hand outlines the graph, this graph is going uphill from left to right, so this is an increasing function. Okay, for number 3, again we have another exponential function. There are no endpoints, so this is understood that these would, the function would have arrows on left and right, so they are continuing on. So our domain is going to be all real numbers, or we can say x is greater than negative infinity, x is less than positive infinity. Now your range this time, our horizontal asymptote is right here at y equals 0. Our function is above the asymptote, so our range is going to be y is greater than 0. As x is approaching negative infinity, that we're looking at the arrow on the left, the arrow is continuing to go up to positive infinity. As x is approaching positive infinity, so we're reading the graph going to the right, we're looking at the right arrow on the graph. This is where it's turning and it's leveling out at the horizontal asymptote, so it's approaching 0. If you trace the function from left to right, notice I'm pulling my hand down, so our function is decreasing. Okay, so for our next two problems, we are asked to graph the function. So we're going to use our calculators to help us out with the graphing. I would go ahead and type the function in at y equals, and we'll take a look at the table of values and try to pick some points that will fit on our graph. If you notice, our graph goes up to 20 on the y-axis, it goes left to -7 on the x-axis, and right to +7. So we have 6 times 0.5 raised to the x power. You should know at this point that this is going to be exponential decay because our number that's inside the parentheses, this number here is less than 1. So we know we have exponential decay. You can also see in just a moment when we graph this that the graph is decreasing. So now I've gone into second graph to see our table of values. My calculator came up where x is -5, but my y-coordinate is 192. So that is not going to fit on my graph. The first point that I see that fits on my graph is -112. So I'm going to go left 1 and up to +12. My next point is 0.6. So that's going to be our y-intercept. We have 1.3. 2 and 1.5. I'm just going to estimate that. 3 and 0.75. Mike can get one more. Let's see what we have next. And then 4, so it's just gradually getting closer to the x-axis. So it's leveling out. Make sure on your test you have some exact points plotted from the table. We do expect you to try to draw this as precisely as possible. Okay, going over to number 15, we're going to do the same process. Again, when you look at your equation, you should be able to determine that this is exponential growth because our b value this time is greater than 1. So when we draw the graph, we should see our graph curving and going up to the right. So I'm going to go back to y equals. We'll clear out the last equation and type in the new equation. And now go to our table of values. So let's see. So we can fit these points. Again, they're decimals, so we're just going to have to kind of estimate them. But if we go left 4, our y value is 0.79, so it's just going to be a little bit below the 1. And then negative 3, 1.18, that's just going to be a little bit above the 1. Negative 2, 1.7, so we're getting closer to 2. 2, let's see, I've lost my place, sorry. 0, 4, wait, I skipped negative 1. Negative 1, 2.6, so just a little bit before the 3. 0, 4, so that's our y-intercept. 1, 6, so right 1 up 6. 2, 9, so we're going right 2 and up 9. We may be able to fit a few more. Let's see what our next value is. We have 3, 13.5. Here's 13, so here's 13.5. And then our last one is 4, 20.5. So I know our graph only goes to 20, but we can just go up a little bit above the 20. So this is our function. So again, we see that our function is increasing from left to right. So we start on the left side. As I trace back over the line, we're going uphill from left to right. So that is exponential growth. Okay, for number 16, it says explain how you know whether any function is exponential growth or decay. So if you're looking at the equation, you should recognize that if b is greater than 1, the function is growth. Now remember, with exponential functions, we don't have to say a negative number. It's the b value. So if the b value is between 0 and 1, so if b is greater than 0 or less than 1, that just means b is between 0 and 1, the function is decay. And remember, we call, if it's a number that's less than 1 but greater than 0, we call that a decay factor. And if it's a b value greater than 1, we call that a growth factor. Okay, we're going to look at some application problems now where we will actually see that growth and decay factor in the equation. Number 17 says Anna's car was worth $26,000 when she purchased it. The value of the car depreciates at a rate of 12% per year. So the key word that jumps out at me is the word depreciates. Depreciates does mean decreases or decay. So remember, when it's decay, I can't spell. When it's decay, we need to convert the percent to a decimal and we need to subtract it from 1. So 12%, remember a percent is out of 100. So if you want to calculate this on your calculators, you would say 12 divided by 100, and that's going to give you decimal 12. It just basically takes your decimal and moves it 2 places to the left. So to find the decay factor, you're going to say 1 minus 12 hundredths, and that's going to equal decimal 88. So we're seeing a decrease of 12%, so 88% of the value still remains. So your equation is going to be y equals 26,000, that's the starting value of the car, times 0.88. And for the first question, they want us to calculate how much the car is worth in 3 years. So you can do the calculations on your basic calculator screen, or you could type the equation in at y equals using x as your exponent, and you can see the answers for both. So if you want to do that, that might be actually a little bit easier. So we can go to y equals, we'll type in 26,000, that's the car's starting value, times 0.88, that's the percent of the value that still remains. And you're not going to put a number here. You need to raise it to the x power. Now when we look at the table of values, we can find any value for x. So when the car is 3 years old, you will see that the car is worth $17,718. Okay, for part B, it asks how much is her car worth in 7 years. So now we can just keep scrolling down in the table. When x equals 7, we find that y equals 10,626. Now, if you don't feel comfortable using the table of values, you can just calculate this on your main calculator screen. You would just type in the 26,000 times the 0.88 raised to the third power, and that's going to give you your answer for part A. And then if we round, and if you do cents, this would be 27 cents. If it does not specify what to round to, we are okay with you rounding to the nearest dollar or to the nearest cent as long as you round correctly. Okay, and then for the 7 years, you would just say 26,000 times that decay factor 0.88, and we would raise it to the 7th power. So that's the 10,600, and you'll see the table rounded it up to 626. If I was going to do the nearest cents, I would have to change this back to 625.57, or I'll leave the whole dollar. That was 10,626. We would accept either of those answers unless the question specifically tells you what to round to. Okay, in number 18, it says a bank account that starts with $8,000 and accrues 6% interest yearly. How much money is in the account after 10 years? So I see the keyword here is accrues, and that does mean that it increases or grows. 6% as a decimal, again, take 6 divided by 100. That's going to be decimal 06. Now, when it increases, you take and add this to 1. So your equation is going to be y equals 8,000 times 1.06. And they want us to calculate the amount in the bank account after 10 years. So you're going to put 10 for your exponent. Okay, we're going to calculate this. We have 8,000 as our starting amount times 1.06, and we're raising it to the 10th power. So if we round this to the nearest dollar, that's going to be 14,300. We will round that up to $327. Or if you round to the nearest cents, we would say $14,326.78. Okay, on number 19, we're moving into the sequence problems. It says the sequence shows the number of Christmas trees a nursery plants each year. It starts at 1, then 12, then 144, 1,728. Which formula could be used to determine the number of trees the nursery will plant next year? Remember, we've talked about writing sequences in the form of next equals now, and we've shown you today and Friday how to convert the next to the a sub n plus 1. Now is the same thing as a sub n. So we need to identify the pattern. I see these numbers are getting large really quickly, so I suspect that this is exponential data. Remember, you can work backwards in a pattern by using division. So if I start with 1,728 and divide by 144, I get 12. 144 divided by 12 is also 12, and 12 divided by 1 is also 12. So we see that we have a common ratio of 12. So we just need to find the answer choice that says the next term in the sequence equals the now term times 12. And that's going to be answer choice A. So then we could find the next term in the sequence by taking the 1,728 and multiplying times 12. Okay, number 20, we have a student error problem. So it says a student claims that the next term of the arithmetic sequence is 18. So we have the sequence, and think about what arithmetic sequences do. They either increase by adding the same number or increase by subtracting the same number. So from 0 to 3, that's an increase of plus 3. From 3 to 6, that's plus 3. So if we continue the pattern, 6 plus 3, the next number should be 9. This student claims that it's 18. So what error did the student make? So hopefully you recognize the student multiplied the 6 by the 3 instead of adding the 3. So the student multiplied by 3 instead of adding. So they mistaken the sequence to be a geometric sequence. They used a common ratio instead of a common difference. Okay, in number 21, we're asked to write a recursive formula for the sequence. So remember that word recursive just means the recurring pattern. So what are we doing each time from one number to the next? Recurring pattern. So we have 48 to 24, 24 to 12, 12 to 6. I do recognize my numbers are getting smaller. So that means we are multiplying by a decay factor or a number less than 1. If you think about the relationship of 24 to 48, 24 is half of 48. So we're multiplying by 1/2 each time, or 0.5. So the common ratio would be 0.5 or 1/2. So we need to identify the recursive equation that says the next term equals the now term times 1/2. And you should recognize that that's going to be answer choice B. Here's 1/2 times a sub n. Okay, for number 22, it says we're given a sub 1 equals 3. Remember, that just means the first term. So the first term in the sequence equals 3. The formula next equals now minus 7. Find the first 4 terms. Hint, a sub 1 represents the first term in the sequence. So you're going to start off with the 3 because that's the first term in the sequence. And they tell us that to find the next term in the sequence, we take the now term and we subtract 7. So we're going to say 3 minus 7, so that's negative 4. Negative 4 minus 7, so negative 11. And negative 11 minus 7, so that's negative 18. So the first 4 numbers in the sequence are 3, negative 4, negative 11, and negative 18. Okay, in 23, we are given the arithmetic sequence 6, 13, 20, 27, and we are asked to write the explicit formula for the sequence. Remember, the explicit formula is either going to be in the form of a linear equation, y equals mx plus b, or you can write this in sequence notation, a sub n equals the common difference times the number of the term, and then plus the a sub 0, which is your y-intercept. Whichever equation makes the most sense to you for this part of the test, you may use either method. So we're given a sequence 6, 13, 20, 27. The first thing I'm going to look at is the pattern. So I see that this is increasing, and I know it's arithmetic, so it has to be an addition pattern. So what would I add to 6 to get 13? And that's plus 7. Let's make sure it works all the way across. 13 plus 7 equals 20. And 20 plus 7 equals 27. Now, we have found what is identified as the slope or the common difference. So we know our slope in the equation, I'm just going to use the linear, is y equals 7x. Now we're going to take the sequence and work backwards. Since this is the first term, we need to know what term comes before that. That would be our 0 term. So if I say 6 minus 7, that is negative 1. So our y-intercept in the equation is negative 1. So our final equation is y equals 7x minus 1. Now that we have the explicit equation, part 23a says find the 25th term. So all I need to do is substitute 25 in for x, so 7 times 25, and then once I have that product, 175, we're going to subtract 1. So the 25th term in the sequence is 174. The 100th term is 7 times 100. That's 700 minus 1. So the 100th term in the sequence is 699. Make sure you study how to set these equations up, because if you miss that equation, it's also going to cause you to miss part 23A and 23B. So if it's arithmetic, you need to know that rate of change, the common difference, and then you work the sequence backwards one time to find the y-intercept. Okay, for number 24, we're given the sequence negative 250, negative 50, negative 10, negative 2. Find the next term. So we're looking for the next term. So I need to identify the pattern. I notice these numbers are changing pretty rapidly, so that makes me think that this is exponential or a geometric sequence, so I'm just going to work backwards and divide. So negative 2 divided by negative 10 is 0.2. Negative 10 divided by negative 50 is also 0.2. Negative 50 divided by negative 250, that also equals 0.2 or 2/10. So I see we do have a common ratio. So now in order to find the next term in the sequence, I'm just going to pick up at the negative 2. I'm going to multiply times 0.2. So negative 2 times 0.2. So the next number in the sequence is negative 4/10, or we could convert this to a fraction. Math, enter, enter, and that's negative 2/5. So we would accept negative 4/10 or negative 2/5. Okay, the common ratio, we actually found that by dividing. So we found that the common ratio was 0.2. We could have also converted that to a fraction. 0.2 as a fraction is 1/5. So we would accept 0.2 or 1/5 as the common ratio. Okay, for 24B, they want us to write the function rule, the explicit formula for the sequence. So remember, the explicit formula for a geometric sequence is going to be an exponential function. We need to know the zero term, so we need to work the sequence backwards one time. B is the common ratio we just identified in 24A. That's that 0.2 or 1/5. And then we raise this to the x power. So the only information we're missing is the zero term. So if you look back, our first term is negative 250. We were multiplying by 0.2. So if we work backwards, we will divide by 0.2. So jump back on your calculators. Negative 250 divided by 2/10. And that gives me negative 1,250. That's going to play the role as your A value in this equation. So our equation is going to be y equals negative 1,250 times 0.2, or you could have 1/5 here, raised to the x power. And now we're going to use the equation in 24B to find the 7th term in the sequence. So we're going to say negative 1,250 times 2/10, and we're going to raise this to the 7th power. So we get negative decimal 0.16, or let's see what this looks like as a fraction. Math, enter, enter. So negative 2 over 125. And again, we will accept the decimal or the fraction answer for the sequence problems. Okay, for number 25, it says suppose a population of 80 crickets doubles in size every 6 months. How many crickets will there be after 5 years? So let me move this up just a little bit. Okay, so our starting amount, this is going to be exponential because we see the word here doubles, and when we double, we're multiplying by 2. So this is going to be an exponential equation. Our starting population is 80 crickets. We're going to multiply this times 2. We need to be careful, though, for our exponent. It says they double in size every 6 months, and we're doing this for 5 years. So understand there would be 2 6-month increments in a year, so we have to multiply the 5 years times 2, so this will be raised to the 10th power. So we are going to calculate 80 times 2 raised to the 10th power, and this comes out to, wow, 81 6,920 crickets. Okay, guys, we're almost there. We're looking at number 26 now. It says the value of a $1,200 computer decreases 35% annually. What will the value of the computer be in 4 years? When will the computer be worth less than $250? So this is a great equation where you would want to actually put it into your calculator and look at your table of values so you can see exactly what year it becomes less than $250. Let's look back at our keyword here. Our keyword is decreases, sorry. 35% as a decimal is decimal 1. Decimal 35, I'm thinking ahead of myself, sorry. So it's going to be 1 minus decimal 35. And that's going to equal 0.65. So our decay factor is 0.65. Now the computer's value starts out worth 1,200. It's now only worth 65%. And we're going to just put an X for the exponent so we can type this into our calculators. So if you go to y equals, we're going to type the equation in, 1,200 times decimal 65 raised to the x power. And now we're going to take a look at the table of values. So we're going to look at 4 years. So in 4 years, the computer is worth $214.21. Okay, and the question said, when will the computer be worth less than $250? So that's actually going to be that year 4, because in year 3, it's still worth $329.55, and year 4 is when it falls below the $250 mark. So we're going to say 4 years. Okay, in number 27, it says the graph of the function f of x equals 4 to the x power. If you look at our answer choices, it crosses the y-axis, it crosses the x-axis, it intersects neither axes, or it intersects both axes. So the easiest way to do this problem is just to go to y equals. We're going to type the function in, so 4 raised to the x power, and then we're going to just go to our graph. Give that just a moment to graph, and you can tell that the function actually only intersects the y-axis. Remember, it looks like it comes down and intersects the x-axis, but because there is a horizontal asymptote there, it's like a wall, the function never actually equals 0. So the correct answer is going to be answer choice A. Okay, for question 28, it says, suppose you deposited $1,450 you earned from a summer job into a savings account that pays 4.2% interest compounded annually. How much will you have saved in 3 years? So again, look for that. Pays means it's going to increase. You still need to move your decimal. 4.2 divided by 100. That's going to give us decimal 0.42. And since it's paying, we are going to add this to 1. So 1 plus decimal 0.42. And that's going to give us the growth factor. So your equation is going to be y equals 1,450 times 1 decimal 0.42. And they want to know how much money you have saved in 3 years. So we're going to raise this to the 3rd power. I'm just going to do this calculation on my main calculator screen. So 1,450 times 1 decimal 0.42 raised to the 3rd power for the 3 years. And we will have $1,640.48 in the account. Okay, we're on our last problem. Our last problem says solve the system of linear and exponential function. Write your answer as an ordered pair. Hint, use your calculator. So remember, when we see that word system, that just means we have 2 or more equations. The solution to a system is always the point where the 2 lines or functions intersect. So we're going to go to y equals on the graphing calculator. On the first line, we're going to type in the linear equation, 3x plus 2. And on line 2, we're going to type in the exponential equation, 2 times 0.5. Oops, I left my decimal out. Raised to the x power. Make sure you have the equations typed in correctly. and then hit graph. So we went to y equals on the calculator, then we went to graph. Okay, now we're going to hit second trace 5 for intersection. And then to get the calculator to actually calculate the intersection, you just press enter 3 times. So enter, enter, enter. I know you guys have heard me say a million times, second trace 5, enter, enter, enter. Second trace 5, enter, enter, enter. Make sure it says intersection on your screen so the two functions intersect at the point 0, 2. So that is the solution to the system of those two equations. They both equal 2 when x is 0. Thank you guys for your time and good luck on your Unit 4 exponential functions test.